radiation, that does come up quite a lot. So, have you done this experiment, Connor? Or at least seen it?
I don't think so.
Have you not? Have you seen the diagram that always goes with it?
I haven't done it. I might have seen it, but I'm not sure.
They always do this diagram, don't they? So alpha, beta, and gamma, right? And then your detector. Now they just do a big detector just to show you the, how it works in the diagram. They do paper over here, and then they do a thicker aluminium, and then an even thicker lead, PB for lead. And then they normally show you this. They go, and by they show you, I mean your school teacher show you. So they go, alpha will be stopped by paper, beta will go through paper and normally stopped by aluminium, and then gamma can go through lead but might not be as much. Alpha can also be stopped by a few cm of air. I don't want to shut my window because it's warm, but it seems to be a helicopter outside, which is loud. Right, a teacher wants to demonstrate that the radioactive source emits alpha, beta, and gamma. So already we should be thinking, right, that diagram is something that you just have to learn. It's a knowledge thing. So should already be thinking alpha, right, I know what to do. And just to kind of help you along, they have said you've got a thin sheet of paper and you've got a thick aluminium sheet, 3 millimeters. It shows the equipment they've got: radioactive source in a holder, a radiation detector, and a count rate meter. So describe a method that they could use. So this is kind of like another one of those smart G kind of things, yeah? So there's nothing against you just writing that on a spare piece of paper. So I normally say state chemicals when it's chemistry, but because this is physics, we're going to state the sources, the radioactive sources. We're going to measure, and that'll be the count rate, I think, because that's what we've been given. Also means method. Oh, who have we got here, I wonder? Hello. Just in time-ish, because I know you want to go through one of these as well, don't you, Amina? Sure I added you. What happened? She came and she went. Maybe she'll try again. Yeah, so measure, then you'll have a method. As long as you've written a method, you should be all right. That's your apparatus. Make sure you mention it. She's in now. I would just say now this one would be right up your street. So the result, or what we're going to record. So we're going to record count rate and test again. So we probably want to do them ×3, and we want to do it with the different sources, don't we? The different sources. So what are your thoughts, Connor, on now we've done that little bit of planning? How would you start this?
Probably set it up first.
Yeah. How about we going to answer that question, though? I want to demonstrate that the source emits alpha, beta, and gamma.
Talk about the properties.
So how can you show it with what you've been given there?
Alpha particles only go a few centimeters in the air.
So would you use air as one of the things, even though it's not been mentioned, would you? Yeah.
I'd talk about it not being able to penetrate the paper, and then because it can only go a few centimeters in the air.
Yeah, well, that sounds good to me. And then how would the count rate be involved, Louis?
I'm not sure since I didn't have a proper physics teacher last year. Would it be how many times the alpha particle gets to the count rate?
Do you want me to explain a bit of the background of this then?
Yes, please.
So if you've got a radioactive source that gives out all of the radiation, what you can do is put a detector in front of it, and then that detector, when the radiation ionizes the metal inside the detector, it will give an electric current, right? So the count rate counts like a piece of current as one count. So it will do that, and it'll just keep clocking up. Now, if that's really close, there's nothing stopping any of the radiation, is there? So you would get quite a big count rate. If you put a paper in front of it, you would probably expect, if it is producing alpha, what would you expect, Amina?
I'm not really sure.
Okay. Connor, what would you say?
I'm not sure either.
Okay. Well, what you would expect is you'd expect the count rate to go down. If you're blocking it with a piece of paper, the beta can still go through, the gamma can still go through, but the alpha will be stopped. So say if your count rate was 1,000, it might go to 900 because it's blocked out some of the alpha now. And then aluminium, if you put that in between, that will definitely block the alpha, because if it's stopped by paper, it's definitely going to be stopped by aluminium. And that should also stop the beta. So at that point, you should only be getting gamma coming through. So it would drop again. So if you were doing this, you'd expect to see two drops, wouldn't you? One when you've taken out the alpha, one when you've taken out the beta, and then you can't do any more with what they've given you to make it go to zero. It's not about making it go to zero. It's about just saying it's got these three in it. So it's just a case of making that now into a method that is, going to give you the evidence for that. So I would personally, because it's not mentioned air, I wouldn't talk about the air. So how do we take air out of the equation? Because alpha can be stopped by air. How can we take air out of the equation so that air is not stopping the alpha? What could we do, Connor?
Move the paper closer.
Not the paper, but the radioactive source. If you move that closer, like almost so it's next to the detector, then that should do it, right? It won't have much air to go through. Yeah, bang right. So number one, we would put the radioactive source, very close to the detector. And once we've done that, what shall we do now, Louis? Once we've put it really close.
Would you measure the count?
Yep, so you just note down the reading. So we're going to measure a reading. So note down the count reading. Now, are we going to do it after 1 second, 10 seconds? What we're going to do, because if you just say note it down, it's constantly moving up. And obviously you can probably see a problem. If I do the first one for 10 seconds and the next one for 20, then I will not have comparable results, will I? So what would I have to do, Louis?
Would you do it at like regular intervals?
I could if I wanted to do a graph of it, but I'm not that interested in a graph. I just want to know how much I've got in a certain time.
I'm not sure then.
Well, I kind of led you to the answer there. That's probably why you're struggling, so I've kind of given you it. So note down the count reading after a minute, for example, after 1 minute. Now, these things will just keep counting forever, right? So you do have to reset them in between. So What I would do is number 3, I would keep the distance the same. Why are we keeping the distance the same, Amina?
So it's the same when you repeat the experiments.
Yes.
It doesn't interfere with the results.
Yes, reliable, making it reliable. You've got to do things that make it so that if you did it again, you should get the same answer, right? So keep the distance the same and put the piece of paper between the source and the detector. Now we've done that, we should probably reset our detector, reset the detector, and measure the count again after a minute. Would we want to say, what was I thinking then? Would we want to say, just repeat all that? Do we want to write it out again? I don't see the advantage of either. So, I see I'm running out of space. Repeat then, and this time with aluminium. So we don't have to write all that out again. Now we've got one recording for each source there, haven't we? So I suppose the final thing to do is repeat the whole thing a total of 3 times, right? What's the point of doing that 3 times, Connor?
So you can work out an average.
Yeah, repeat a total of 3 times. So calculate an average, because I'm going to have to get another piece of paper here, because radioactive decay is, what word am I going to put after is, Louis?
Random.
It is random. So you won't get the same number every time. This is the bit I was trying to say earlier, and I just totally forgot how to say it. Are we going to say what we would expect to see, do you think? What do you think, Amina? Would you say? And if it's worked, what you'll see is, so explaining the results.
Would you talk about the higher number of clicks per minute, the more the radioactive substance emits?
Well, we're actually keeping the same radioactive substance, aren't we? So it should be pretty constant. You normally use one with quite a long half-life, so you can assume it's pretty constant. They have like half-lives of millions of years, some of these things. I'm thinking more in terms of, are we going to say, so when you put the paper in, this is what you should see. When you put the aluminium in, this is what you should see. When you have nothing there, this is what you should see. Who would be inclined to do that now? Or would you leave it there? Connor, would you do that? Would you explain what results you might get, do you think?
I'll probably explain the results.
Yeah, so let's do it then. So let's say when the paper is there, you would expect alpha to be stopped and see a fall in the count rate. And then I would explain what that means. So this proves alpha is present. When the aluminium is there, which ones do we expect it to block this time, Louis?
Beta.
Any others?
And alpha.
Yeah, so alpha and beta should be stopped. Why does everyone say beta anyway? I've often wondered that. You're not the first. Must be on the videos. Do they pronounce it like that on videos you've seen? And the count rate would drop further. And then the last thing, I suppose, we would still see a count rate because the gamma's still going through, right? So there should still be a count rate as gamma can pass through all of these materials. Have I missed anything that anybody thinks needs to be in there, just unmute yourself if you think so. 3, 2, 1. Okay, I'll assume we've done all right then. So let's have a look then. Obviously, these are in levels. Would not lead to a valid outcome. Would not necessarily lead to one, and then would lead to one. So I think this would lead to one. So move the detector very close to the source, record the count rate. So these are not just like a mark per thing, but I do tick them. So we have put very close, note the count rate. We have put after 1 minute. That wasn't mentioned in that. Position the paper between the source and the detector, record the new count rate. Alpha radiation will not penetrate through paper. If the count rate with the paper is less, then we've got alpha. Right, so have we got all those things? Put the piece of paper, yeah, and measure the count rate again. Have we got this? When the paper is there, you would expect alpha, and then see a fall in the count rate. This proves alpha is present. Yes, good. Next bit, remove the paper, do the aluminium, record it again. Beta will not penetrate, count rate falls. So it's the same thing as alpha, but for the aluminium. So we have said that. We haven't got to the repeat bit yet. We expect a fall, yeah. The experiment should be repeated and mean results calculated because radioactivity is a random process. Nice, we've done well there, haven't we? Definitely said random. And we definitely said the averages. So that is how we get 6 out of 6. Now, we stated our sources. That's what we did. We measured this count rate. We've done a method. We've talked about the apparatus. We've recorded the count rate ×3, and we've changed the sources. So that smart G thing we did right at the start has helped us out big time there. If you miss out the apparatus, you're going to struggle with some of those marks, aren't you? So that's why those are there, just to help you. But not everything is a smart G, though, is it? There are some other kinds of questions, and I suppose we'll look at one of those. Right. Do you want me to scroll through a few to give you some choices? I'll read them out. So we've got this one about transferring energy and specific heat capacity. We've got this one. So this one is the one that doesn't come up a massive amount. So it's normally in the 2 or 3 mark questions, but it's about the plum pudding model and the gold foil experiment. And then we've got one that's a graph data analysis. And then we've got one that's about trolleys, which is from the EdXL paper, which appears on EdXL paper 1 and AQA paper 2. I have got it again, a different version of this in the other half on paper 2. So if you don't want to do it here, it's still there. So we can do it either way. So what are we thinking, Amina? Which do you prefer? Are you trolleys, plum puddings, graphs, or calculation?
The graph or the trolley? I think
Yeah.
the trolley.
What are you saying, Louis?
Calculation.
Yeah. Connor?
Probably the graph.
So we've got, I think graph's won then out of that, hasn't it? As I said, the trolley thing comes up again, so we can do that that trolley thing as part of paper 2, and you can just see the difference. Right, figure 1 shows how the mean power output from solar and wind energy resources in the UK varied between 2014 and 2019. Right, so I kind of like to do a bit of a joining the dots on these, just to give me a bit of an idea of how it goes. So that's definitely going up. We had a dip, didn't we, in 2016? And then for this other bit, which is solar power, that's gone up. Oops, bit curly, that one. Not up so much there. Yeah, so wind's definitely gone up at a faster rate than what solar has. And then let's have a look at our other graph. Figure 2 shows the power output from solar and wind energy resources varies in a typical year. So wind, I'll do in pink. So wind's generally going down until July, then it goes up to a peak in November, then down. What you've got to imagine is that line would continue back to there, wouldn't it, for the next year. So because we've got 1 year, it just chops off. And then green, I'm going to do solar power. So generally speaking, it's gone up. We've got a plateau there, and then down again. Kind of obvious reasons. It's generally windier in winter and it's sunnier in summer, right? That's kind of what I'm getting from that. So, explain the changes in power output from solar and wind energy resources between 2014 and 2019. Now, I always make sure that those numbers are actually on the graph, because I've definitely been caught out before where it said some years, and it turns out that those years are only part of the graph. So you've just got to be mindful of that. So explain the changes between 2014 and 2019. You should include an explanation of the change in power output during a typical year. So we're looking at both graphs, aren't we? So how do you think the mark scheme might work on this, Connor? What do you think you're getting marks for? Is it like 3 marks for 1 point, 1 mark for a point? What do you think?
Probably 1 mark for a point.
Yeah. Any other thoughts on that, Louis?
I think if you explain 1 point like really well, you can get 2 marks on 1 point.
Now, you've picked up on the command word there, which I think is important. So you've picked up on that. Explain the changes. It's power output. We're comparing solar and wind. And then we've got the years. So, Amina, first thoughts on this. What might you put for your first sentence?
I'd make an overall statement on solar power and wind power.
Yeah,
So
let's do it.
or shall you write, or shall I stop?
I'll write it and you tell me.
So as solar power is the dark. Okay, as solar power fluctuates. No, as solar power slowly increases, wind power fluctuates but slowly increases because wind dips more.
I've got some advice for you. This is to do with how much power output you're getting from wind and from solar, right? So what we've got is we've got more power output from wind year on year, except in 2016 where it went down. Now, I suppose if you dig into that a bit, you can kind of make a judgment about 2 things. Number 1 thing is how windy it was in a particular year. Now, I would have said UK on average over a year probably going to be about as windy every year, unless there's like a hurricane or something. So there must be something else going on here that means that the power output's going up. And I think that's probably the thing to talk about. So what might that thing be that's making the power output from wind go up if it's not more wind? Sorry, I should have asked somebody. Connor.
I'm not too sure. Might just be the weather.
All right. Louis, what do you think?
I'm also not too sure about this.
Oh, really? Amina?
If it's not the weather or the wind, would it be fuels? I'm not really sure.
So this is a big
someone-
trap question for everybody, isn't it, really? It's a massive trap, because for each of you, you could start going, well, it was windier this year, then it wasn't as windy that year, which may or may not be true. But I'd have thought on average, it's probably going to be roughly the same. So the only thing I can really come down to is that, and you probably go, oh, I can't believe I didn't think of that. I would bring it down to they have built more windmills and they have built more solar panels. Are you all doing that noise? Okay, well, you are allowed to unmute when I ask you things. So I would start with the power output from wind. Wind has increased. And then an explanation why this will be due to, or this is due to. We might include that there might be more wind. This is due to there being more wind. And more, what are they called? Turbines, aren't there? More turbines being built. So using that as kind of like the model, Louis, do you want to have a go at commenting on the solar power?
So during winter, there's like more cloud coverage above the UK, and also due to like Earth's rotation around the sun, it means that there's less daylight to get to the solar panels.
Can I come back to you on that one when we do the second graph then?
Yeah.
Okay, Connor, looking at the first graph, what can we say if we write a sentence that's very similar to the one I've just written about the turbines?
There's more wind turbines getting built.
About solar power, sorry.
There's more getting built, like placed.
So the output from solar has increased slightly. It's not a lot, is it? So we just put this is due to it being sunnier, maybe, or an increase, or shall we reword that, or more solar panels being built. Now, there's an interesting kind of summary of that. If we've just written two things there about there being more wind and it being sunnier, what might that be down to? There's kind of like an overarching kind of reason as to why that might be. What are we saying, Louis?
I'm not sure.
Amina?
Could you repeat that again? I'm just a bit confused with the graph.
I'm going to reword it then. I'm going to say, is there something going on in the world that means there will be more wind and more sun?
Could you say climate change?
Yeah, so you could tie this into climate change. So power output might have gone up due to climate change. That's just what I thought. Because if both have gone up, I mean, we don't know if they've built more or not, do we? But we can kind of argue two different things on here. So power output may have not increases, may have increased due to climate change. Yeah, that's good. So let's start then talking about what happens in a typical year. And I'm going to come to you, Louis, for that.
So during the summer months between like May to September usually is when we've got the most sunlight here in the northern hemisphere. And then so essentially there's also less cloud coverage since it's a lot warmer. And which means there'll be more sunlight to go power the solar farms.
I always think of it as more concentrated sunlight.
Yeah.
But also there's something else in summer, isn't there? The length of the days.
Yeah.
So, and days are longer. So how do we tie all that together? During the summer months in the northern hemisphere, we have less cloud coverage and days are longer. So what we're saying? Which one does that affect? Wind or solar? Still with you, Louis.
You've lost me.
So you've said to me during the summer months in the northern hemisphere we have less cloud coverage and days are longer. So we need to link that to something that answers this question. You should include an explanation of the change in power output during a typical year. So that graph there is our typical year. We've done the explanation, but we haven't said which one that actually refers to. Is it referring to wind or is it referring to solar?
Refers to solar because there's
So,
more concentrated sunlight.
Yeah. So during the summer, we have less cloud coverage and days are longer, meaning solar output is higher. Yeah, does that make sense now?
Yep.
That's good. Okay. So, who would like to have a go at talking about the wind over the year? Connor?
I didn't quite catch. I was writing this down.
All right, well, you carry on writing down then. Amina, how would you talk about the wind? So we're basically describing the line, aren't we? We're saying, you know, it goes up here, it
Yeah.
goes down there. This is why.
Could you see for wind power is it in July the power is 2000? This could be due to intense heat or humidity, therefore the wind turbines don't move.
I'm not 100% sure the connection there, but I've no doubt you would get credited with it. I mean, this is probably drawing in something that you've learnt in geography, right?
Yeah,
So I would just put in July, the power output is,
rapidly decreases.
well, I'm just going to put it's at its lowest around, what's that? Looks like 1,900 megawatts. And we're saying that's due to like a lack of wind. Yeah, I wouldn't go into explaining how weather systems work and stuff like that because I think it's too much. I just missed something out from Louis earlier. I wanted to put that in there due to more concentrated sunlight. I know it's small. Right. Have we kind of covered everything there? Is there anything that we might want to add? I think there's one thing I might want to add. I don't know if you've spotted it, have you, Connor?
No, I thought they were all good, to be fair.
I mean, it is good, but we haven't really said about when wind is at its highest, have we? Amina?
Could you talk about when they're both at the same points?
You could. I don't know if that's. We're talking about the changes, aren't we? I don't know if.
They
I don't know
wouldn't
if it
work.
matters too. I mean, we've talked about when sunlight's at its highest. We've talked about when wind's at its lowest. I mean, I would just want to, make sure that the ball is in the back of the net properly and just cover the fact when sunlight's at its worst and when wind's at its highest. That's the only thing I would want to finish off with. So just for the sake of getting an answer down now, I would say sunlight or what is it, solar? Solar is the lowest in winter due to lower concentration of sunlight and shorter days, meaning lower output. And then I would just do the same for wind. Wind is at its highest. I should have really put output before. Highest output in the winter months. I liked what you did earlier. I can't remember who did it. Might have been Louis. And you started talking about the months. So like November, December, January. November to Jan, when it's windiest. So, you know, when you do a description and an explanation and you say, you're talking about a line going up and down, say, oh, look, it's gone up and it's because of this. Can you see how you've got another potential to score marks by also saying when it's the lowest as well? You're just covering a few more bases there. I mean, say this is 2 marks for every explanation. Every bit of colour there, 2 marks for the pink bit, 2 marks for the red bit, 2 marks for the blue bit, 2 marks for the black bit, 2 marks for the red bit, and there's possibly 4 marks available in that last bit, because I've done 2 bits there. We're just hitting everything, aren't we? You know, and I think it's a bit like just, you know, firing off a load of bullets and hope that some hit. You've just got to put as many solid points down as you can, just for the off chance that maybe one of the things you've written, you just missed out a keyword or something. I know we're trying to hit them, but there's always a chance we've missed 1 or 2. So let's have a look. Relevant points, reasons, causes, right. Output from wind increased because more wind turbines were built. So, oops, hello, we don't want to be rubbing it out. So, yeah, we did say that being built. Oh, that was like 2 points. So, noticing it's increased, and then also that it's because of turbines. Solar output increased, more solar panels were built. Okay. Does it mention the weather as well? Power output from wind and solar may have increased due to climate change. Well done. Was that a meaner? So for 2005 and 16, wind power was lower because it was less windy. Now, we forgot to talk about that, didn't we? I know we did mention it, but we've probably got enough in all the other bits and bobs. For most of the year, the electricity generated from wind is greater than solar. I know we haven't covered that. Greater in winter than it is in summer, yeah. Because in winter it's windier than summer, yeah, so that were these bits. Yeah. Electricity again from solar is greater in summer because the sunlight is out for longer. Intensity, we've definitely done that. I almost messed it up actually. And then it says to access level 3, the answer should describe trends in both graphs and in solar and wind power and give some explanation. So I think we've solidly done that, don't you? Only thing we missed out was that little change, but we've hit that many of the other ones that I think it'd be crazy if that didn't get 6. But if we'd have not done this bit at the end, so this bit, I think we'd have been struggling, don't you? Right, let's have a look at the paper 2 stuff, because we've spent a lot of time on that, but they were very wordy answers. Probably want to do some calculations, don't we? Right, here's some calculations, right, because these are nice and fast. Figure 11 shows a car being driven at a constant speed past a speed camera. The camera recorded 2 images that are 0.7 seconds apart. The car travelled 14 meters, so that's a distance. Distance can be S or D, can't it? That's a time. The maximum deceleration of the car is 6.25 meters per second squared. Calculate the minimum braking distance for this. What's your go-to when you see a question like this then, Connor?
I'd write down what I have and then find the calculation I need.
Yes, so where would you get these equations from?
The equation sheet.
Yeah, so this is an AQA one, so we'll look at AQA. So it's not a kinetic energy, it's not elastic. They're all electrical ones. Right, this looks more like it. Then we've got acceleration, changing velocity. So it could be that, couldn't it? We've got distance there, it could be that. We've got final velocity, acceleration. So it's probably one of those three, right? Can't see any others it would be. So let's go back to what we've got. We've got an S, which I think is a distance in that one, yeah. Distance travel is speed times time. So that is an S. That is a time. So, right, minimum braking distance. So this seems like I can do it in one equation. I don't know if that seems right. So, where would we go with this, Louis? What would you do?
I'd pick like the correct numbers from the thing. So it says
You would use that, would you? S equals VT. Yeah.
so
There you go.
I'd first write the equation out that I'm going to use, and then I'm going to put the numbers into the equation.
Yeah. Stay with me then. So S equals VT. Then we go, the S is 14 meters. Do we know the velocity? I don't think we do we? So it looks like we're working out a velocity here. This is where it starts to make a bit more sense, right? And then the T is the time. So times by 0.70. Do you agree with that?
Yeah.
Yeah. So if we rearrange those, we do V equals 14 meters divided by 0.70 seconds. I don't know why, but that looks like it'll work out quite nice. Connor, what have we got for that?
2 seconds. I didn't. 20.
20, yep, I got 20 as well. So 20. Right, I'm going to let you in on a little secret here, right? If you're not sure of what your units are, do like what I've done here. I've included them all the way down. So I've got M and S. So I've actually got, if I just split that, I'll just write it over here. So I've got 14 over 0.70. I've got M divided by S. So I now know that my units are going to be M divided by S, which is, as we know, meters per second. So that's just one way of doing it if you're not sure what you've got. So now we have a velocity, don't we? We've got a velocity of 14 meters per second. We have an acceleration of 6.25 meters per second squared, which means every second that was decelerating by 6.25 meters per second. We do have a time as well. I don't know if that's going to be important, but I'm going to rewrite it. I don't know if we need to use it again. We might do if we calculate in a force maybe later. So back to this. Acceleration, changing velocity, time. Do we need that? We want a distance, don't we? That's the only one left with a distance in it. Is that what we're looking for, a distance? Calculate the minimum braking distance as it passes. Right, yeah, so we've got the velocity now, acceleration, driver time, don't have the braking distance. Yeah, that distance before was a distance between the images being taken, wasn't it? So that's why we got the velocity right. So if we go back to this, we've got v squared minus u squared equals 2as. That's the only one there that's going to help us, I think. So let's just write it up here. V squared minus u squared, was that right? Equals 2as. Now, there is something that this question has told us without telling us. What has it told us without telling us? I know this is a bit of a weird question, but what have we been told without actually being told? What do you reckon, Amelia?
I'm not really sure. Is it one? No, could it be decelerating?
It is decelerating. We were told that. What happens at the end of a deceleration?
Eventually stops.
So you've actually been told what the final velocity is.
Always zero.
It is actually zero, isn't it? So it told you without telling you. You do get this a lot in these kind of questions. So I think this is the most hidden I've ever seen it on this question. And the bit that really sealed it for me when it said calculate the minimum braking distance, didn't say when it's become stationary, didn't say when it stopped. But a braking distance normally has a stop, doesn't it? So that's the only thing that I could actually work out from that. So if we're going to use this, then it's not V, is it? That's actually the U. That's the initial velocity. V is the final, which is zero. So I think we've got everything there. So if we put these numbers in, so V squared equals, sorry, not equals, minus U squared is 2AS. We can go 0 meters per second, take away 14 meters per second, and all that is squared, equals 2 times 6.25 meters per second squared times by S. And that's the thing we're working out, S, isn't it? So I dare say we can just get rid of that. So we've got minus 14 meters per second squared divided by 2 times 6.25. Oh, sorry, what have I done that? No, sorry, not 14 meters per second. I meant to have written 20 there, don't I? That's meant to come from there. You all let me do that, you know. So, it might just be worth thinking about. Because this is a deceleration, I might just put a minus there. So then these signs make a bit more sense. So what I should have is 20. Not going to make a difference, is it, when I square it? But 20 squared divided by 2.625. That's 12.5, isn't it? So I've run out of room a little bit, so I'll have to do the equals along there. So 20 squared, what's that? 20 squared, is that 400, is it? Yeah, 400 divided by 12.5. And hopefully we'll get a decent answer. So divided by 12.5, has anybody done it? Yeah, Connor?
Is it 32?
Sounds good to me. Let's see what number this question was. 6.3 late on means it's hard, right? So 32 is the answer. Normally they give you full marks if you've got the right answer, but they do want to see some working. That was not easy though. I was kind of thinking on my feet whilst I was doing that. It was tricky. Has anyone got any questions about what we did there then? Any bits that they don't quite get? Okay, I'll assume we are happy. So because this is on paper 2 for AQA and paper 1 for Edexcel, I might just do the Edexcel version just because I know we've got somebody here who does Edexcel. So in all AQA, the questions are very similar anyway. It's the same kind of idea. So if we do this one, it's not a massive problem for anybody. Okay, so this one, like I say, it's on Edexcel paper 1 or AQA paper 2. And it's a trolley investigation. A student investigates the effect of a crumple zone on the force exerted during a collision. The student has one trolley with a spring at the front, another without a spring. The student uses the arrangement in figure 10. After the trolley is released, it accelerates down a slope and bounces off a rigid wall. The speed of a trolley can be measured just before a collision with the wall and just after a collision with the wall. The silver foils are connected to a millisecond timer. The silver foils make contact with each other during the collision, so the time they are in contact can be read from the millisecond timer. Explain how the student could investigate the effect of a crumple zone on the average force exerted during the collision. Your explanation should include how to determine the force. You may wish to refer to an equation from the list of equations at the end of this paper. How the effect of a crumple zone may be shown in investigation. Precautions that may be necessary to achieve accurate results. So I suppose we should have a look at the equation sheet. So the Excel one's slightly different. I think F equals ma is going to be important, and I think acceleration is going to be important. So we're going to use them too. So I think if this is smart G that we can use for this, I think as S is going to be stating the equation. We're going to measure, Mr. G off, measure the times and the method of doing that. Apparatus, obviously, that's listed there. Result is the average force. T, we're going to test, well, you probably want to do it 3 times. And then G, go again with the 2 trolleys. So what would I do to start with? So if we're going to determine the force, we've got these 2 equations. We've got F equals ma. We've got acceleration is v take u over t. So we're trying to find out A. We can get that from using a balance. So acceleration, if it's going to, said somewhere about measuring the speed just before and just after, so it will give us that. So that's good. So if I'm putting this into a method, let's go for no spring trolley. So what we want to do is, number 1, you want to weigh the trolley with a balance and note down the mass. Then release trolley and obtain, I suppose it's 3 things: speed before impact, speed after impact, and the collision time. Because what you would expect is, if there's no spring, it'll just hit it and bounce off. I expect a really low contact time. And then if you do it with a spring, it'll hit it, squidge, and then squidge out and get a longer contact time. And that will spread the force over a time. We'll see that in a second. So once we've done that, we would show how to measure the acceleration. So acceleration is v take u over t. So for example, you might get, so I'll just do this in a different color because it's an example. They haven't given us this information. I'm just kind of making it up on the fly. So you might get something like it's minus 1.4 meters per second. So it's going to the left. Take away what its speed was going to the right, so 2 meters per second possibly. It would make sense. It would make sense for it to be a lower velocity afterwards, and then divided by how long it took. So we could say it might take something like 0.02 seconds. So whatever that is when you work it out, let's have a look. Minus 1.4 take 2. I should have known that. Minus 3.4 divided by 0.02 gives you minus 170 meters per second squared. Okay, so once you got that info, you've got an acceleration. So whatever your mass was, let's just assume the mass was something like 0.8 kilograms. You would then just use an equation. So after that, you go for force equals mass times acceleration, which equals 0.8 kg times by minus 1.70, 170, not 1.70 meters per second. So 0.8 times 170 is 119 newtons. So that's just a kind of an example. So you would say use that to calculate the force. Now, it does mention this, how they affect the crumple zone. So what you would expect is with, well, not rib with, but repeat with spring. So you'd expect a longer impact time. So kind of assuming if all that was the same. So for example, if that was exactly the same, but a longer impact time, so something like 0.080 seconds, what would that give you? So that'd be minus 3.4 meters per second over 0.08 seconds. What would that give us? Minus 3.4 divided by 0.08, 42.5. And then you would do that times by 0.8 kilograms. And that should give you minus 34 newtons. So just by putting the numbers in, you can kind of tell that you get a lower force if it takes longer to hit in contact with the wall. So the effect is a longer impact time gives you a lower force. So that'd be 0.6, I think, on there. So then we're just left with precautions. So you'd have to have the same height ramp, same length. Can't really think of much more. But you can see, can't you, that number there and there decides how big that number and where did I put it, and that number is. And with a spring, just numbers made up off the top of my head, it shows that you get a lower force. And that's important. If you're in a car crash, you want a lower force so you don't get injured as much. You still would get injured, but not as much, I would have said. And then just looking at the mark scheme, what bits have we done? So use F equals MA. So we've used that bit. We've used keeping the slope same. Oh, we didn't say repeat, although I did mention it in the Smart G. So repeat times 3. And then you've always got to put and average. Spring as a crumple zone, never mentioned that. Measure the trolley masses, yeah. Different contact times, same starting place. Well, that's the length, isn't it? So yeah, I mean, that's how you get 6 on that. Don't be in a mad rush, and then you can just check these things off. We've done the 2 trolleys thing. Whoops, 2 trolley things 3 times. I did mention it eventually. Measuring the force. Yeah, we have mentioned any apparatus we wanted to use. Timings, and we've used the equation. So there you go, 6 marks. Nice.